Hello everyone, my name is Morimoto, Vice President and Chief Technology Officer of IBM Japan. Today, I'm very honored and pleased to be able to share with you the IBM recent development and progress of IBM Quantum programs. Before I begin, let me explain a little bit about the background of why we're doing this. As we all the world is facing a lot of the critical issues for human being. Not to mention about the food, energy, transportations, and mobility. We're all facing into the serious pandemic issues as well, and that threaten the human's health. That's been said, we are all been facing to the situation that the science has never been stronger and demanded than ever in the world. And in order to advance the science, the discovery of a new technology, new materials are very, very critical. So we have been focusing into several key technologies to drive that. One is AI, the artificial intelligence. The second is computing, in general, including the classical and future computing. Third is the importance of data, not just the amount or mass of the data, but the quality of the data. And number 4 is the infrastructure. More specifically, the computing infrastructure, including the hybrid cloud and the data connections, IoT, sensor networks. Now let's focus on computing. IBM is viewing the computing as these categories. The first, bits. Second is neuron. And third is qubit. In the bits, it represents the classical computer advancement, mainly driven by the semiconductor transistor shrinkage. IBM has been doing this area of research since the beginning of the computing era, almost half century ago. And we start with the micrometers scales of semiconductor transistor shrinkage down to now into the nanometer scale of shrinkage. IBM has just announced the state-of-the-art, most advanced semiconductor chip in 2 nanometer node. With this later technology called GAA nanosheet, we'll be able to fabricate transistors as small as less than 50 nanometers. That is about the half of the diameters of the coronavirus. And we believe that this technology will take us even further to the single nanometers or even smaller scale and higher performance, lower energy of the chips. However, that alone is not enough. On the other side, we're also advancing the AI technology that associate with the neuron. One area is the software and algorithm side. We developed the AI called Watson, and it shows the world that what AI and computer artificial intelligence could do in the Jeopardy quiz show in 2011. And later, you've seen the advancement of artificial intelligence in many areas, including the machine translation, visual recognitions, and more. But all of that actually still focusing to so-called narrow AI, which is the single domain, single task. Complete and accurate data set is required for the heavy training, and problems that we can address that is the only problem that has a single and accurate correct answers. Instead, we need to focus on much broader capability of AI, which is the broad AI. Multi-domain, multitask. Machine can train and be learning even with the incomplete and insufficient set of data. And we need to focus on the problems that not necessarily has a one single accurate answers. So those technology advancement all is going to drive the machine computation power necessity. Even today, with the growing number of data, the computational requirement in the world has been increasing 2x every year. That is very, very significant amount of computing power that we need. So we need advancing the new way of computing, new technology, new chips, and particularly for the AI workload. So that's a second group of technology that we're focusing on in Neural. Even that, it's very clear that IBM and human being is going to run out the computation power really, really soon. So we need to come up with third element of future computing, that is quantum. Now let's talk about quantum. Quantum computing is based on very unique capability called quantum mechanics. More specifically, two very unique aspects. One is called superpositions. The other is called entanglement. Superposition will allow us to build the quantum bit, qubit, that has the capability to be able to represent more than two states at the same time. It's different from the current bits, which can only represent 1 or 0, single state at a time. Instead, quantum bit or qubits can represent more than one states in the probabilistic states. That is superposition. And entanglement will allow the multiple qubits to entangle and influence to each other, either straight same bit flip or the negative bit flip. No matter how far those two qubits are, once they've been entangled, they'll be associated together and reflect each other's movement. And this is called entanglement. With the combination of these two unique quantum mechanics characteristics, we'll be able to build the quantum bits, quantum circuits. And those circuits will have much more diversified and unique capability to represent the mathematical representations on computer that has never been possible before with classical computers. By combining those qubits, we'll be able to create the quantum circuits called quantum gates. In classical computer, we have a gates called AND gates, NOR gates, NOT gates, and those gates, we have about 7 fundamental gates. Instead, in quantum gates, we already have more than 20 different quantum gates we can combine to build the circuits. And that will become much more rich representations on quantum circuits. In the classical circuits, you can only represent one state at a time. Instead, in the quantum gates circuits, you'll be able to represent much more diversified and rich mathematical representation with a smaller size of bits. And by combining those quantum gates, you'll be able to build the more complex quantum circuits called quantum algorithms. And that will be the constructing building block for more complex quantum problems, such as simulating quantum systems for physics, chemistry, material sciences, or algebraic problems such as machine learning, differential equations solving, and factorizations. Another areas called quantum search, that including the quantum Monte Carlo simulations, optimizations, and graphs. All this, it may look or sounds like very complicated, but from the user point of view, it's just as simple as running on a piece of software on computers. You can still use your own computers connected to the networks by just running your own Qiskit algorithms on Python or any other languages you like, and use that to call the quantum algorithm into your circuits or programs to run it. And once it's connected to the quantum computers, your programs will be compiled into the signals that have been sent to quantum computer, and quantum computers will translate that into microwaves signals that is going to send directly into the quantum bit to run the quantum circuits on the computers. And the result will be measured coming back and all the way back to your computers as the answers. That's so simple. You don't have to even worry about what is running behind these machines. Now, in order to advance these whole research areas, of course, we need a lot of work to do. One area is scaling the hardware. The other is building the quantum cloud platforms that allows people to access to the quantum machine much easier. The other way is build the application tools for quantum developments. So first, in the hardware side, let's take a look at the inside of the quantum computers. In IBM, we use the superconductive quantum bits that has the chip been built inside the refrigerators called dilution refrigerators. And all the way chip is installed at the bottom of the refrigerators, which has been cooling down to the 15 millikelvins. That is almost minus 273 degrees, absolute 0 degrees. It's the coolest place in the universe ever. In order to drive the computation on these qubits, we need to use a microwave. Therefore, in the other side, you see the microwave generators and microwave controllers. And then your computer program will be running on the cloud and then taking into this microwave controllers to convert that into the microwave to be sent into the qubit underneath these dilution refrigerators. The key components are the chip itself, and that is very obvious. So IBM is building this quantum chip based on many of our accumulated semiconductor packaging technologies that we have been doing for a long time. In 2019, we released a 27-qubit chip called Falcon. It with the very optimized lattice structures. Last year, we announced a 65 qubits chip called Hummingbird. It will have a scalable readout capabilities to improve the readout values and stabilities. This year, we announced 127 qubit chip called Eagle, with a novel packaging and control improvement of electronics around this. With more advanced semiconductor-based technology to miniaturize the components and packaging and integrate all the circuits, we're aiming to announce the 1000 qubits chips called Condor by 2023. And this chip, now then we can stack this 1000 qubit chips to get the multiple thousand chips, eventually get to much larger size of quantum bits. The quantum machine's capability is not solely represented by the quantum bits. It including the noise levels and also the capability to be able to compute longer circuits. And with all the capabilities and quality, we measure this as and called it the quantum volumes. In 2019, IBM announced the roadmap of quantum volumes that we committed to improve the quantum volume by 2x every year. So we wrote the roadmap and announced it. And before 2 years, we are already advancing this roadmap by announced much more higher quantum volumes machines or chips earlier than scheduled. So we'll continue doing this progress, and we're very confident that we'll be able to achieve or overachieve this roadmap we laid out in 2019. Which means that everybody using today's quantum computers can actually start to imagine, if you can do this with today's quantum computers, what will be possible 2 years later, 3 years later, or 5 years later? And you can confidently think of that you will be able to get that level of hardware performance up within a certain period of time. Therefore, you can imagine or start to assess what will be possible in what years in your area of applications. Now, in order to advance this, it's not only the qubits and chips. We need to also advance a lot of the surrounding electronics, including the cables, microwave attenuators, amplifiers, materials, and packagings. And ultimately, we need to build the much bigger diffusion refrigerators that can even have a human inside. It is called super fridge in IBM. And we're building the very unique, very large diffusion refrigerators as well. Now, in order to advance the quantum computers, it's not only the hardware or chip or system side, right? We also need to build the computational platforms, software platform to support the developers or researchers to use the quantum computer without knowing or learning too much about the complexity of quantum's algorithm itself. So the compiler layer, runtime layers, and those are cloud accessible algorithms and open source softwares are very, very important. But we have been piggybacking on this advancement that we have been doing in the last half centuries or so. And we don't need to wait that long to have this on quantum scale. We can just tap into those most advanced cloud systems, open source system, algorithm sharing, and software sharing platform right now. So with this, we'll be able to build quickly about those shared platform for the developers in order to advance our research communities and research activities worldwide. One of the first industry academia collaboration has started in Japan with Keio University. At the time, the dean of the School of Engineering, Professor Ito, has teamed up with IBM to start the IBM Quantum Hub at Keio University with 4 private companies and about half dozen of researchers there. Well, he's a true visionary. So 2 associate professors at the time was promoted to full professor after the success of the launch of this quantum research center at Keio. And Professor Ito himself was actually been named as a president of Keio just this month. And that research center is now grew into the very large size of quantum research activity center, including more than 30 scientists and 7 private companies to join. They're mainly working on those 3 areas. One is quantum chemistry or material sciences area. The other is from financial risk assessment and risk management area. And the other, one of the most pervasive and popular areas, including the artificial intelligence and quantum machine learnings. And later, in Taiwan, we also have the NTU join IBM to open the Q Quantum Hub in Taiwan, NTU. And that has also grew very rapidly with a lot of active research themes coming up from there. So I'm also looking to see more progress from there as well. And now this style of a quantum hub activities in the worldwide has grew into 7 or 8 new hubs coming up. Most of these partners, we call, are using the most advanced IBM quantum computers throughout the networks. Just as of the March this year, overall, we have more than 250,000 users on these quantum systems and run over 500 billion quantum circuits. We have built more than 30 quantum computers, and more than 20 quantum computers are hooked active online and has more than 97% utilization from overall more than 140 clients and partners accessing to these machines. IBM recently announced one of the most strategic and advanced partnership in US with Cleveland Clinics. This is to agree the 10 years long-term research partnership, including the providing the more than 1,000 qubit quantum machines on-site to Cleveland Clinic with all the research collaboration and activities. We believe this is going to be one of the model case to drive and accelerate the science and discovery. In Japan and Germany, last year we announced the 2 major announcements of quantum computers. It is to install the first commercial-based quantum computers outside of the United States. In Germany with the Fraunhofer, and in Japan with the University of Tokyo. In Japan, we're going to install the 2 quantum systems. One is IBM Q System 1. It's the first commercial quantum machines, and we're going to install in Shin-Kawasaki City in Japan. It's going to be dedicated to more than 12 of our local partners, private companies and universities for their own research activities. But the partner can only also access to more than 20 activity connected network computings in the US. The second quantum systems is going to be installed in the University of Tokyo, which is for the experiment and test and study of the new materials or temperature electronics and surrounding components to build the future quantum computers. Now, with all those partnerships and technology advancement of quantum are very important, but there's nothing more important than building the next generation talent and people. IBM is also committed to provide the education and brought up the next generation scientists or mathematicians or computers, for the worldwide, young generation people. We have been running a lot of the quantum hackathons worldwide. And last year, of course, it was run on digital, but we run the Quantum Hackathon Challenge in last year. And with more than 3,000 people participating from 85 countries, it's probably one of the largest online quantum events or hackathon event that we run before, but very active activities. Now what I'm most proud of is the number one prize was won by the Japanese students from university. And also many Asian students, kids participated on this, including those from Taiwan. So I'm very, very proud of it, and I'm looking for the more active participation from the school, from the industry, to drive these very exciting technology areas that matters to all of our lives. Now last, I'd like to show you this short video to end my speech. Thank you very much. And please stay safe, stay healthy.